Let's look at the board once. This is lecture number 5. Again, this is a continuation to the previous class only. So MOSFET basics. Okay. In the last class, we have seen, okay, how to identify the source and drain terminals of a NMOS transistor and PMOS transistor, right? Okay. So what are the symbols for this one? Symbols of NMOS and PMOS. Okay. So this is what we can say. This is the NMOS. This is a PMOS. Okay. Which side is NMOS? This is the NMOS. This is a PMOS. Okay. Now I'm going to ask you, for example, I'm going to give you different cases and please let me know which one is the source and which one is the drain. Okay. For example, let me take this is the one option. Okay. Okay. And then paste here. Okay. And I'm going to take something like this. For example, this is the 5 volts I'm applying here and 2 volts I'm applying here. -5 and 3, 2, 7, -6, -5. Okay, if I give something like this, okay, the terminals I've given something like this. You tell me, okay, I'm not, of course, definitely I'm not focusing on the gate terminal. So gate is already, we have seen that there's the gate terminal, but only we focus mainly problem with the source and identifying the source and drain. Why? Because the reason is that source and drain have the same material. There is no, they both are indistinguishable. Okay, we have to apply the potential, then only we came to know that which one is the source, which one is the drain. Okay, right, right. What we can do here now? How do we know this? And one more thing. Okay, yeah. Let us pick what is the source and what is the drain. So high potential is always at the drain side, and this is the source. What about this? This is the source. This is a drain. What about this? This is the source. It's a drain. What about this? Source. This is a drain. Okay, not that by using that particular symbol arrow marker, you should say that there's a source, right? Depending upon the potential that we apply, we should say about that, right? Now, what is the current direction in this case? Can anyone help me? What is the current direction? So this is the current direction. In this case, here, bottom, here, drain to source, here, and also drain to source. Okay. But in general, we always try to write something like this. Okay. So the moment if you write, whenever you would like to use the MOS transistor in our circuits, you please write, we would like to use in this fashion only. Okay. This is not only the telling the, it is not only telling that it is an NMOS transistor, arrow mark, it is also saying for the source. That means we would like to always connect the arrow terminal should be at the source. That means low potential you apply, and high potential you should apply at this place. This is what the conventionally we follow. Okay, but the behind the scene, this one actually should not say directly because of the arrow mark this is the source, because the arrow mark is not this drain. You should not say like that. Depending upon the potential, you should say. Okay, right. Similarly, we'll take another one. Okay, similarly, we'll take the PMOS as well. Let me take copy here. PMOS. We take some few examples. Okay. Okay. Now let us consider this is again -5, -2, 7, 3, 2, -5, -2, -2. Okay, can you please tell me which one is the source and which one is the drain in this case? How do we, if it's a PMOS or NMOS? Not because I have written the PMOS and NMOS, okay? Okay, you should say based on the arrow mark, right? Okay, so therefore, what about this is PMOS, of course. Which one is the source and which one is the drain? High potential is at the source. Okay, high potential. This is the high potential, right? It's the source. This is the drain. What about here? This is the source, drain. What about here? Source, drain. What about here? Source and drain. Okay, you have to say in this way. What is the current direction in this case for the PMOS? High potential to low potential. High potential where it is from source to drain. What about here? Source is at high potential. Here, source is at high potential. Here, also source is at high potential. But always conventionally, what people will write here, conventionally we follow this approach. Okay. Okay. This arrow mark is not only for PMOS representation, it is also for source potential. Okay, this is the drain potential. Drain terminal, sorry, so it's drain terminal, source terminal. Okay, but conventionally, if the example problems they have given, they have to identify that. Otherwise, conventionally, we follow that the arrow mark is meant for PMOS as well as the high potential we apply at that particular terminal in our circuits. Okay, this is the way we should remember. Okay. Okay. And let us see. Let us see some mathematical models for the electronics components so far we have seen. What are the different components we have seen so far? What are the components? What are the electronics components so far we have seen? A resistor, okay. Resistor that we have seen. A capacitor we have seen. Maybe inductor we have not seen, but we'll see a little bit later. Okay. Next, the diode that we have seen. Okay. The MOSFETs that we have seen, right? So these are the components so far we have seen. Okay. Now we would like to we would like to understand about the mathematical models for these particular components. Okay. So what do you mean by a mathematical model of any element or any component? What does it mean? What is a mathematical model? What do you mean by a mathematical model? It is very simple actually. Okay. to understand the behavior of any component, okay, what generally we do? Generally, in the electronics components, you're finding the current and voltage, nothing else, right? Okay. If you say that, okay, if I give you some component, then you will go to the lab, right? You will go to the lab and apply the potential and find the current. Okay. For the different values of the voltage, you find the different values of the current you will get into. Okay. You'd like just like a draw the diagram and you say that, okay, if I'm applying the input voltage something like this, the current is flowing in this way, maybe increasing or decreasing, or maybe whatever the direction it can go based on the readings that you can say. Okay. So this is what you have to identify the characteristics of any component. Okay. But in general, what we can do, we don't want to waste our time to go and do this kind of things. Okay. First of all, we want to model that thing. Okay. What is the modeling here? We are doing mathematical model. That means we have to develop some mathematical equations to govern the behavior of that particular component. Right? Okay. So therefore, that mathematical model always gives you the what is the behavior of that particular or characteristics of that particular component, similar to that of the characters that you have derived in your experiment, the physical experiment. Are you get the point? Okay. Now, without going and do the experiment, okay, what the result could be, the same thing can be obtained by using the mathematical equation. Okay. So that by looking at that equation, that you can say that, okay, suppose if the current voltage is providing the voltage, then the current will be going or increasing or decreasing or some other fashion. By looking at that equation. Therefore, it is required for analog designers that what is the mathematical model of the components that you're using in your circuit. Once you know that one, then you're able to estimate its circuit behavior. Okay. So have you heard about the spice modeling? Okay. So what we can do normally, we take one software. Okay. It is allow you to write a Verilog, which is allow you to write the spice code, or it may be connect the components. And the spice tool, what it will do, it will take the mathematical model of each and every component. Okay. By applying the stimulus to it, it will be evaluated based on the particular mathematical model of the circuit, and it will produce an output. Okay. So therefore, the mathematical modeling is an important aspect for any component before going in reality how it will work. Okay. So therefore, we have to understand about the mathematical modeling of all these five components. Okay. Since actually we are talking about the IC design, right? Okay. IC design means that even if you have a resistor, even if you have a resistor can be implemented by using the, the transistor. Capacitor also can be implemented by using some kind of capacitor. The MOSFETs, MOS capacitors we can use there. Okay, definitely the active element is always replaced by the transistor, and current sources also can be replaced by the MOSFET. That means everything can be, the IC can be full of MOS transistors only. Okay. So how a MOSFET can be realized by used as a resistor, all these things we'll see in the coming classes. For the time being, just to understand about IC design is all about develop the circuit exclusively with MOS transistors. Okay. Okay. So let us take one simple mathematical model. Okay. For a resistor, for example, let us consider. Okay. Can someone help me? What is the mathematical model for resistor? Okay. Assume that we have a resistor here. Okay. Apply the potential difference here. Suppose some R is here. Apply the potential difference V. Okay. What is the result that you can expect? Current which direction it will flow? High potential to low potential, right? Okay. Now, what is the current if I want to expect? And keep on increasing the voltage. What should be the current? That's what its behavior, right? Over the period of time, how it behaves with respect to the input is nothing but a behavior or a characteristics. Okay. What is the behavior of yours? If I ask you something like this, then what is your answer? I cannot say just as you're looking at you and say that this is a behavior. Not that, right? Over the period of time, how you are behaving. That means throughout this semester, how you are behaving. Based on that one, I can say that this is what this behavior is. Right? Okay. So similarly, so uh, what is the mathematical model for this? Okay. So it is nothing but I is actually 1 by r times b. This is what the mathematical model. Okay, I'm not going to deal with how it came about. Okay, simply you remember that. Okay, this is what the mathematical. So that means what is its how it will be represented graphically? Okay, something like this. Okay, as you can see, it is a linear relationship between I and B actually. If you increase the voltage of a particular resistance, sorry, something like this. It's a linear element. Okay. Okay, particular resistance value. What is the slope of this line? Can someone tell me what is the slope of this line? The slope is 1 by r. Therefore, if you apply the V here, if you calculate what is the I, it always, as long as you're increasing the voltage, the current through the resistance will increases for a particular resistance value. If the resistance value is smaller compared to, for example, this is the R1. Okay. Okay. If the R1 is less than whatever the R2, for example, the R1 is less value, what will happen? Where the curve should be towards this vertical direction or horizontal direction. If R is high, what will happen? That means a small resistance value. R is less means what? Less resistance value. If the less resistance value, what will happen to the current? More current will flow, right? In this equation, the slope of this line is 1 by R. If the R value is less here, if the R value is less here, what will happen? In this particular direction, resistance value, the slope of this line, what will happen to the slope of this line? If the R1 value is less, for example, is less, what will happen? The slope of this line decreases. The slope of this line is decreases. So 1 by R I'm writing, right? If the R value is smaller and smaller, for example, what will happen to this one? The slope of this line will decreases. Oh, sorry. Is the decrease means slope of this line is increases, right? So if it is increases means the slope is increased. Slope increases means where it has to move towards the y-axis. Okay. So therefore, this value this is moving